picking up good vibrations.
Let us compute the Fourier transform for a given example. This example is a rectangular discrete time signal which equals 1 in the interval from minus capital N1 until capital N1 and 0 outside this interval. We have already computed the Fourier coefficients for a discrete time periodic wave, and the tricks that will be used here are very similar to the tricks that we used there. In this video, the explanation of some steps will then be shortened. Here we simply have the formula for the discrete time Fourier transform. There are three differences with respect to the formula for the discrete time Fourier coefficients. First, the limits of integration are now from minus infinity until infinity. Second, we do not divide by capital N, which was the period for periodic signals. And third, we now have e to the power of minus j omega n, whereas in the formula to compute the Fourier coefficients, ak, omega was replaced by 2 pi over capital N k. Since xn is equal to 1 in the interval from minus capital N1 until capital N1 and 0 outside this interval, we can replace the limits of the summation from minus capital N1 until capital N1. We will now apply a change of variables. We will make m equals n plus capital N1, and let us see the new limits of the summation when n equals n1, capital N1, and n equals minus capital N1, m is equal to 2 capital N1 and 0 respectively. Besides, when we replace in e to the power of minus j omega n by m minus capital N1, we get e to the power of minus j omega m minus n capital N1, and we are left with this expression. Now, since the exponential of the sum is the product of the exponentials, we can write e to the power of minus j omega times m minus capital M n1 as e to the power of minus j omega m times e to the power of j omega capital N1. Since we are adding over m and e to the power of j omega capital N1 does not depend on m, we can take it out of the summation and move it to the front of the summation, meaning that this factor will multiply each value of the summation. We now have a factor multiplying a summation from m equals 0 until 2 times capital N1 of a geometric series, where the ratio of the geometric series is alpha equals e to the power of minus j omega. We will now apply the formula for the summation of a geometric series. A crucial fact is that we can only apply this formula if alpha is not equal to 1. And this means that e to the power of minus j omega cannot be equal to 1, which entails that omega cannot be 0 or a multiple of 2 pi. Since we only need to consider this formula over a period, say from minus pi until pi, the only critical point will be omega equals 0 that will be addressed in the end. We will now rewrite the numerator and denominator in the fractional part of the expression using the fact that 1 minus exponential of minus z equals exponential of minus z over 2 times exponential of z over 2 minus exponential of minus z over 2. We apply this with z equals omega times 2 capital N1 plus 1 in the numerator and z equals omega in the denominator. After replacing the formula, we get several multiplying factors, the one that was already there in front of the expression, one in the numerator and one in the denominator. These will all cancel out. In fact, if we multiply the factor in front of the expression, e to the power of j omega capital N1, with the factor in the numerator, e to the power of minus j omega times 2 capital N1 plus 1 over 2, this will lead to e to the power of minus omega over 2, which is exactly the factor in the denominator, and these two will cancel out. We obtain this clean expression. Note that e to the power of jz minus e to the power of minus jz equals sine of z times 2j. Therefore, we will apply this fact to the numerator with z equals j omega times 2 capital N1 plus 1, and z equals omega over 2 in the denominator. We obtain this expression where the factor 2j appears both in the numerator and in the denominator, and we will cancel the factor 2j, obtaining the final expression. In one of the steps of the derivation, we had to consider omega not to be 0, so we still have to consider the case omega equals 0. This is rather simple. When omega equals 0, then e to the power of minus j omega n is 1, and we are left with the summation of xn in the interval from minus capital N1 until capital N1. Since x of n equals 1, we simply get 2 times capital N1 plus 1. As a final note, if we compute the limit as omega converges to 0 of the general expression we obtain for the other values of omega, we obtain the same value, 2 times capital N1 plus 1. This is often why you will see that the discrete time Fourier transform of a rectangular wave is simply written as sine of omega times n1, capital N1 plus 1 over 2 over sine of omega over 2. Although the function is not defined when omega is 0, it is implicit that it can be extended by continuity. That is, we can take the limit as omega converges to 0 and obtain 2 times capital N1 plus 1. Let us now compute the discrete time Fourier transform of a one-sided discrete time exponential given by a to the power of n times the Heaviside function u of n. By multiplying by the Heaviside function, we ensure that the resulting function is 0 for negative n. Thus, we only need to consider the summation from n equals 0 until infinity, and since the Heaviside function in this interval is 1, we can remove it. We have also grouped the terms a to the power of n and exponential of minus j omega n into a single term, a e to the power of minus j omega to the power of n. We get then the summation of a geometric series with ratio alpha equals a e to the power of minus j omega from 0 until infinity, and we have a formula to compute this, which basically tells us this summation is 1 over 1 minus alpha, provided that the absolute value of alpha is less than 1, and this is ensured by assuming that a is less than 1. We then get 1 over 1 minus a e to the power of minus j omega, and this is the final expression. The resulting discrete time Fourier transform is now complex as the function is not even, as opposed to the previous example. Since it's complex, we should plot either the real and imaginary part or the absolute value and the phase, and here at the bottom you see the absolute value and the phase. Let us now compute the discrete time Fourier transform of a two-sided exponential given by a to the power of the absolute value of n. After simply applying the formula, we notice that we can partition the summation from n equals minus infinity until infinity into two summations, the first from n equals 0 until infinity, and the second one from n equals minus infinity until minus 1. In the first summation, since n is non-negative, we can remove the absolute value. In the second expression, since n is negative, we can replace the absolute value by minus n. Let us apply a change of variables to the second summation. Let us call n bar equals minus n, and replace accordingly the limits of the summation to 1 and plus infinity, and replace n by minus n bar in the terms that are being summed. We obtain in both summations that they are sums of geometric series. In the first one, we get that the ratio is a times e to the power of minus j omega, and in the second one, the ratio is a times e to the power of j omega. We have formulas to compute the sum of a geometric series, and if we simply apply these formulas, we obtain that the first summation is given by 1 over 1 minus a e to the power of minus j omega, and the second summation is given by a times e to the power of j omega over 1 minus a times e to the power of j omega. We will now multiply the numerator and denominator of the first expression by 1 minus a times e to the power of j omega and multiply the numerator and denominator of the second expression by 1 minus a times e to the power of minus j omega, so that both expressions have the same denominator and we can group them. We can expand the last factor in the numerator and see that two terms given by a e to the power of j omega cancel. Moreover, in the resulting expression, in the last term, we obtain e to the power of j omega minus j omega, which is equal to e to the power of 0, which is 1. Let us now expand the numerator and group two terms leading to minus a e to the power of j omega plus e to the power of minus j omega. From the definition of complex exponential, we know that e to the power of j omega is cosine of omega plus j sine of omega, and that e to the power of minus j omega is cosine of omega minus j sine of omega. If we add these two expressions, we conclude that e to the power of j omega plus e to the power of minus j omega is equal to cosine of omega, and by replacing this fact in the original expression, we obtain the final expression for the discrete-time Fourier transform of a two-sided exponential. In order to compute the Fourier transform of a discrete-time complex exponential, we follow a similar approach to what we did in continuous time. Instead of directly computing the Fourier transform, we look at what is the inverse Fourier transform of a Dirac centered at frequency omega naught. Plugging in this Dirac in the inverse Fourier transform formula, we obtain a complex exponential signal times a constant which is 1 over 2 pi. So if we make the Fourier transform 2 pi times a Dirac centered at omega naught, we obtain the desired complex exponential by inverse Fourier transform. So we know that a single Dirac centered at omega naught in the interval between 0 and 2 pi suffices to obtain the inverse Fourier transform of a complex exponential. Now, since the discrete-time Fourier transform must be periodic with period 2 pi, we have to repeat this Dirac in the intervals from 2 pi until 4 pi, from 4 pi until 5 pi, from minus 2 pi until 0, etc. So that we obtain a periodic signal with period 2 pi. The resulting periodic function is in fact the discrete-time Fourier transform of a complex exponential, since it is periodic with period 2 pi, and if we take the inverse transform that is only evaluated in the interval from 0 to 2 pi, we obtain the desired signal. The last example we will discuss is the Fourier transform of a cosine. A cosine can be written as a real part of the complex exponential and therefore a sum of two complex exponentials, each multiplied by 1/2. Since we have already computed the discrete-time Fourier transform of complex exponentials, it suffices to add the two and we obtain the discrete-time Fourier transform of a cosine, which is also depicted at the bottom.